In the last video, we learned that bag of words and TF-IDF convert words to numbers, but they can't capture meaning. Today, we'll see something that seems like magic: word embeddings. Imagine if you could take the word king, subtract man, add woman, and get queen. That's exactly what word embeddings let you do. These are dense vector representations that understand semantic relationships, context, and meaning. Welcome to the world of Word2Vec and GloVe, the methods that revolutionized NLP before transformers came along. Remember the sparsity problem? With bag of words, if your vocabulary has 50,000 words, every document becomes a 50,000-dimensional vector, mostly full of zeros. That's wildly inefficient. But there's a deeper problem. BOW can't tell that car and automobile mean the same thing because they're treated as completely independent dimensions. Word embeddings solve both problems at once. They represent words as dense, low-dimensional vectors, typically just 300 dimensions instead of 50,000. And these vectors capture meaning through a simple but powerful idea called the distributional hypothesis. You shall know a word by the company it keeps. If cat and dog appear in similar contexts after verbs like pet or feed, their vectors should be similar. This context-based approach is the foundation of all modern word embeddings. Word2Vec, introduced by Google researchers in 2013, uses a simple but brilliant idea: train a neural network to predict words from their context. There are two architectures. First, CBOW, continuous bag of words, takes surrounding context words and predicts the center word. If you see the cat blank on the mat, the model learns to predict Saturday. Second, skipgram does the opposite. Given a target word like sat, it predicts the surrounding context. Skipgram works better for rare words and larger datasets, so it's more commonly used. Training is straightforward. Slide a window through millions of sentences, create training pairs, and update the neural network weights. The magic happens in the hidden layer. Those weights become your word vectors. After training on enough text, semantically similar words end up with similar vectors, purely from learning to predict context. Now for the truly magical part: vector arithmetic. You can actually perform mathematical operations on word vectors and get meaningful results. The most famous example: king minus man plus woman approximately equals queen. Why does this work? Because the relationship between king and queen is similar to the relationship between man and woman. It's a gender transformation. The model learns these relationships as consistent vector directions. Paris minus France plus Germany gives you Berlin, because both are capital of relationships. Walking minus walk plus swim gives you swimming. The model learned verb tenses. These aren't cherry-picked examples. You can find similar words, explore analogies, and discover relationships purely through vector operations. This is why embeddings revolutionized NLP. They capture meaning mathematically. GloVe, Global Vectors for Word Representation, was Stanford's answer to Word2Vec, released in 2014. While Word2Vec learns from local context windows by predicting nearby words, GloVe takes a global approach. It first builds a co-occurrence matrix. How often does each word pair appear together across the entire corpus? If ice and solid appear together frequently, that's captured. Then, GloVe factorizes this matrix to create word vectors whose dot products match these co-occurrence statistics. The beauty of GloVe is that it combines the best of both worlds: the semantic relationships captured by neural methods like Word2Vec, plus the statistical information from global word co-occurrences. In practice, GloVe often performs better on analogy tasks and is faster to train, though both methods produce high-quality embeddings. The choice between Word2Vec and GloVe often comes down to your specific dataset and task. Word embeddings transformed nearly every NLP task. Sentiment analysis saw huge accuracy boosts. Instead of just counting positive and negative words, models could understand that amazing and wonderful are similar. Machine translation improved dramatically because embeddings capture cross-lingual semantic relationships. Document similarity became more nuanced by averaging word vectors into document vectors. Recommendation systems could find similar products even if they used different words in their descriptions. The beauty is that you don't have to train these embeddings yourself. Pre-trained models like Word2Vec trained on Google News or GloVe trained on Wikipedia are freely available. Just download and use them in your projects. Between 2013 and 2015, word embeddings became the default first step in nearly every NLP pipeline, boosting performance across the board. They were so successful that they laid the foundation for modern transformer models. But word embeddings have critical limitations. First, they're context-free. Bank has the same vector whether you're talking about a river bank or a financial institution. Second, they're fixed. One word always gets one vector, losing the richness of polysemy. Third, they can't understand sentence-level semantics. Averaging word vectors for "the food was not good" might suggest positive sentiment because "good" is in there, completely missing the negation. These limitations led to the next evolution: contextual embeddings. Models like Elmo and BERT generate different vectors for the same word depending on context. This was the bridge to transformers, which we'll explore in Unit 2. But don't dismiss Word2Vec and GloVe. They're still incredibly useful for fast baselines, low-resource scenarios, and when you need interpretable features. Understanding them is essential for appreciating how we got to modern LLMs. They prove that meaning can be captured mathematically, and that changed everything.